Next video from chapter 5 is going to be on some specific forces, and this is in chapter 5-7 in the textbook. Alright, so first off, mass and weight. So weight is actually the force, and it's defined as the gravitational force exerted on an object. And weight, and I always like to use F with a little subscript G for weight. Some books like to use a W to stand for weight, but I always like to label my forces with F's and little subscripts. So I use F sub G, so it is a vector, and if you're close to the surface of a planet, say like the Earth, you can find the weight of an object as the mass of an object times the acceleration due to gravity. So if we're at the surface of the Earth, we're going to use 9.81 meters per second squared. And of course, gravity pulls things downward, so the weight of an object is always downward. Now, the important thing to remember is that mass and weight are not the same thing. So remember, mass is a measure of inertia, and weight is the force of gravity. So, well, we're used to using them interchangeably, but in physics they are different. All right, and the important thing then is that since mass is a measure of an object's inertia, it's independent of where the object is located. So if my mass is 100 kilograms, my mass is 100 kilograms whether I'm on the surface of the Earth, whether if I'm on an airplane, whether I'm on a spaceship or the International Space Station or on the surface of the moon. No matter what, my mass is 100 kilograms. Weight, however, depends on the strength of gravity wherever the object is located. So my weight will actually change based on where I am, whether I'm on the surface of the Earth, or whether I'm up in an airplane, or whether I'm on the moon. Okay, so another type of force is the spring force. So spring forces, and sometimes these are called elastic forces, is defined as a restoring force, and it's proportional to how much an object is stretched. So the restoring part comes in because think about a spring, if I stretch it to the right, it exerts a force to the left. Or if I stretch it to the left, it exerts a force to the right. So that's what the restoring force means. It just means that the force is in the opposite direction from how you stretched it. And the proportional bit just means that, well, if I stretch it further, I get a larger force. So the more you stretch, the bigger the force is. So many objects, like springs and rubber bands and all sorts of other stuff, obey what's known as Hooke's law. So Hooke's law says this spring force, and this is F sub H is the notation your textbook likes to use. This is sometimes also used as F sub E for the elastic force. And it's defined as negative K times delta X. So K here is known as the spring constant, and it's really just a measure of the stiffness of your spring. The bigger it is, the stiffer your spring is. And if you look at the units here, the SI units for the spring constant are going to be newtons per meter. So if you have a spring constant of 1 Newton per meter, that says if you stretch your spring by 1 meter, it's going to exert a force of 1 Newton. So delta X, if I go back here, so delta X then is the amount you've stretched it. So when typically we use delta X because your coordinate system may or may not have the origin at the start of your unstretched spring. So the delta X here is how much the spring has been stretched or compressed, and the negative sign here, so that's the restoring force bit. So if delta X, so if delta X is to the right, then the force is going to be negative or to the left. All right, so normal forces, I messed up my animations here. So if you have an object resting on a ground or a table or a desk or a ramp, whatever it is, some sort of a surface, the surface is going to exert a force on it. And if you think about it, it actually has to exert a force on it because typically gravity is going to be pulling things down. And if you set an object on a table, it's not going to crash through the top of the table normally, which means the table, if gravity is pulling it down, there has to be something. The surface has to exert a force upward, and this is known as the normal force. And usually you label this as F with a little subscript N for the normal force. The important thing to remember about the normal force is that the direction of this force is always perpendicular, or normal. Normal is just another way to say perpendicular, to the surface. So let's say you have a box sitting on a nice flat table. So the normal force is going to be perpendicular to the table, which is straight up in this case, and gravity is going to be pulling straight down because that's what gravity does. Now, on the other hand, if you have a box sitting on an incline, so a table that's tilted or a ramp of some sort, well, the normal force is still going to be perpendicular to that ramp. So if the ramp is in this direction, perpendicular to that is off in this direction. But gravity, since gravity doesn't care about ramps, gravity just always pulls things down. So remember, for a normal force, the direction of the normal force is always perpendicular to the surface. Okay, so another type of force we can talk about is tension. So tension is the force in a rope, string, chain, or cable. So, and typically we use F with a little subscript T for a tension force. And the important thing to remember about the tension force is that we usually assume that the rope or string or chain or cable or whatever it is massless and unstretchable. Now, if that is true, and again, typically as long as the rope is fairly thin and it doesn't stretch a lot, these are usually pretty good assumptions. So if those are true, then the tension force has to be the same in magnitude everywhere along the rope, string, chain, or cable. So, and the direction of the tension force is always along the rope, string, chain, or cable. Okay, so then finally we've got kinetic friction. So kinetic friction happens when you have two surfaces that are sliding across each other. So there's also things called static friction and rolling friction, so we're actually going to talk more on those in the next chapter. So for kinetic friction, we're going to use F with a little subscript K for kinetic friction. And you can find the magnitude of kinetic friction as this constant mu sub K times the normal force. So the magnitude of kinetic friction is related to the normal force and this thing mu sub K. So, and remember, this actually has to be the magnitude because normal forces are always perpendicular to a surface, and typically the kinetic friction is actually going to be along the surface. So they're in different directions. So this equation doesn't have any vector arrows because it's only telling you the magnitude. So F sub n, of course, is the normal force, and this mu sub K is known as the coefficient of kinetic friction. So, and it's a dimensionless number which actually depends on the surfaces. So if friction is really, really small, so let's say we have ice sliding over ice. So that's pretty slick. Friction is going to be small, so mu sub K is going to be a pretty small number, maybe like 0.1 or 0.05 or something like that. On the other hand, if friction is large, then mu sub K, like if you have sandpaper sliding on sandpaper, you're going to have a lot of friction, so mu sub K is going to be a large number. So, and typically what you do, there's actually tables of these in your textbook, so if you need to know mu sub K, you'd actually just look it up in a table. So, and then, the equation gives us the magnitude, and the direction of kinetic friction is always opposite the direction of motion. So if you're sliding to the right, the direction of the kinetic friction force is going to be opposite to that or to the left. And we'll actually see, so all of these specific forces, we'll see some examples in class of how exactly you use these.